Por eso que el Vale, yo creo que con el este es el
No, pues espera.
Eso es como la tendría que haber, tiene que haber una primera para todo.
Hay cosas.
No le hace falta.
Pero solamente para
Esos son problemas de personas que los mayores tenemos muchos problemas.
¿Está aquí o no?
No va solo en
¿Cuál es el
Okay. Let's continue. Maybe some parts of this theory has been a little bit boring. I hope to be more enthusiastic in the practical part.
No, it was very refreshing.
No.
Inspiring.
Well, I also need to run a little bit in order to arrive to the more, let's say, practical part. So, obviously, keep in mind that this is only a very general introduction, and we have no time to get deeper, but just you will have the main ideas, and this is enough for the purpose of the course. So, let's continue with this classical example. This is the most classical example of model, the population model, in which we can see the basic elements. This is a influence diagram, a very basic influence diagram of a population, in which we have the main variable, in this case is population, and population will increase according to the birth rate. So a higher birth rate, higher population will we have, and it will be decrease the population with the death rate. So if we increase the death rate, we will have less population. So obviously, if we have more population, the death rate will be increased, and if we have more population, the death rate will increase. So we have two different loops. One loop is a reinforcement loop. In this reinforcement loop means that we will always grow population, grow the rate, grow population, and so on. And we will have a balancing loop. Balancing loop, if we try to increase population, we increase the death rate. But when the death rate is increasing, then we decrease population. So we have a plus and minus. So this is a balancing loop of established stable loop that reach, let's say, an equilibrium point or something like that, usually. So balancing loop is stable, reinforcement loop is unstable, usually. Also, we have, well, this variable will be usually that we will call stock. This is something that we keep. And this will be rate, and rates will be flows. And the flows usually are linked, both flows in this case, with some auxiliary variables. The auxiliary variables, in this case, is the fractional birth rate and the average lifetime. So according to the fractional birth rate, we will have a different birth rate, and according to the average lifetime, we will have a different death rate. Okay? So, well, I'm going to ship other examples because we have not so much time, so let me ship this more or less the complex examples. And going back to the definitions, well, we are going to use three main kinds of variables, three types of variables. One will be stocks. We will use stocks for any kind of variable that we are able to accumulate. Anything that we accumulate, we can represent like a stock. For example, we accumulate a number of rabbits or people, or we accumulate tables, or we accumulate CO2 in the atmosphere. Whatever we accumulate can be represented by a stock. Okay? In the graphical mode, stock we will represent by a rectangle. And flow. Flow will be the variation of the stock. Any variation, any rate is like derivative of the stock. Okay? So all the chains that are produced in the stock, we will try to represent by flows. So usually they are derivatives of the stocks, maybe inflow or maybe outflow. In a mathematical way, stocks will be the integral of the difference between the inflow and the flow. And we can represent in the graphs by a valve sign. And finally, we will use the auxiliary variables. Auxiliary variables are any other thing that we are going to use to represent the system. And finally, clouds. Clouds is just something like a source or sink that they have no name for the purpose of the system. So it's very common to use that we call a hydraulic metaphor to represent. It's quite easy to understand. A tap to fill with water, the deposit, water deposit or whatever. This is the inflow, so the water that is inside go into the deposit, and the outflow, the water that comes out of the deposit. So with this metaphor we can represent anything. In general terms, that, and we have two different and outflow. So the stock in a mathematical way will be just the integral of inflow minus outflow plus the stocks are understand the industrial like stock, how much we have. Obviously, CO2 in a but the CO2 in the atmosphere obviously is a stock, so we have two different flows. The emissions of CO2 is an inflow, as much emissions every year we have of but also industrial capital, you have investment, with time you have a devaluation of industrial capital, so you increase your industrial capital. It's quite relevant when modeling.
What does it mean? There, it was saying that they could be bidirectional, this is not recommended.
Sorry, I don't understand.
By direction.
The flows.
The direction.
Only one direction, the flow is
Bidirectional, but it's not recommended.
Well, you can use bidirectional, but maybe we can choose an example. But when you use bidirectional, usually it's not so unstable. What is meaning in every case. So for pedagogical reasons, you usually recommend, if you have two directions, to use two different flows. For example, in the case of population, obviously you can understand population like births minus deaths. That is quite clear. But obviously you can use only one flow, just for example, net rate of growing, just one flow. Or to have bidirectional, let me, the case of CO2 between atmosphere and ecological system, ocean or forest or something. So move from one to other. This is what you mean bidirectional, isn't it? So you can represent it, but usually it's less intuitive when we are going in one direction, when we are going in another direction. And also, you have a bidirectional, probably you will have an equation that may be positive or negative. You are not going to see clearly when it's positive and negative. So I recommend to have two different flows. Just obviously mathematically it's the same. You can do it if you want, but it's not so clear. But it's possible if you want. So I was talking about the relevance of the units. This is something very clear, but I should mention that the units are very relevant. Obviously, we can use any kind of units, but the units should be consistent, coherent. So if we use population as individuals, births and individuals per year, birth rate, the inverse of year. So in order to maintain the coherence between the units. well, I go ahead. So, and the rest of the variables that we will need, most of the variables that we will need will be auxiliary variables. Before someone asked about how many endogenous and exogenous. In the case of auxiliary variables, let's say 95% of the variables are auxiliary variables, parameters, constants, whatever. So we will have only limited numbers of stocks. Stocks indeed are the real differential equations we have, or the order of the differential equations we have. So each stock means one state variable, one differential equation, however you want to consider. But obviously for any kind of dynamic relation we need a lot of auxiliary variables. So sometimes we can have several stocks in a chain. So from stock 1 to stock 2, in the hydraulic metaphor, imagine one deposit, then another deposit, one flow, other flow, so on. And obviously you can have so many flows as you want, and it can be as complex as you want. Look at, in this case, for each stock, we have here, this is a diagram of the Tom Fiedemann. By the way, if you are interested in certain dynamics, Tom Fiedemann has a free library of models, very interesting, in our web page. You look for Fiedemann invention, I mean. And, well, even he has some EAMs. He has developed, maybe you are familiar with DICE. DICE is well, obviously one of the first IAMs and very famous. Fiedemann also programmed DICE in Benzene. So in this case, I only show you this diagram for the different land uses, green, tree, open, dry, just to show how many flows may be. For each stock, in this case, you have 3 different inflows, 1, 2, 3, 4, sorry, and 1 outflow, 2 outflows, this one and this one. So you may do as complex as you want. And the rest of the variables, you have stock, flows, and many auxiliary variables. All these are parameters, constant, that usually all of them are auxiliary variables. I think I have finished this part, and I started a new one. Topic 3. Okay, I'm going to be quick in this part also. So, most of the dynamics are fairly small numbers of distinct patterns of behavior. That means that most of the systems have similar behavior. The behavior is the way they move, they evolve through the time, independently that they are maybe physical system, economic system, social system, any kind of system. So this kind of, let's say, common behaviors of variables are very interesting to be studied in order to understand what is happening and in order to model them. So the most common modes of behavior we are going to check is the exponential growth. We have already seen this exponential growth with one loop, go to infinite. This is a consequence of a positive feedback loop. The goal seeking is when the system goes to a certain equilibrium. And usually is consequence of a negative feedback loop. This is balancing loop or equilibrium loop, as you want. Another behavior is oscillation. We have shown the oscillation in the case of this shower with hot and cold water, and usually they are consequences of negative feedback. I mean balancing feedback or balancing loop with delays. The delays implies usually an oscillation behavior. Also, a very interesting behavior is that we call S-shaped growth. So at the beginning it's like exponential growth, but later it goes to a limit compared to a value. And finally, we have the overshoot and collapse. Grows, and then after a maximum collapse in a very low value. We are going to see. This is the graphical representation of this behavior. This is the exponential growth, classical reinforcement loop, and stable, goal seeking, maybe decreasing or increasing, but anyway, very a convergence value. So we hope that, for example, when Ilya wanted to discuss about the energy intensity, I showed you that the energy intensity evolution in time is similar to this one. We have decreased quickly, but we see that the rate is every time lower. So it seems that we are going to reach a minimum value, obviously over zero. This is the S-shaped growth. At the beginning, it's like exponential growth. Then we change the tendency, and then the growth is lower until it reaches a, let's say, maximum value, stable maximum value. This is oscillation. This is the growth with overshoot. So there is a growth, then some oscillation behavior, and finally reach a maximum value or a stable value. And this is the overshoot and collapse, a very growing rate, and then a quick decrease. So let's show some examples of behavior. This is a very simple case with a stock, one inflow, one outflow. Let's start with an inflow rate of 100. So every unit time we will have an input of 100 units. It doesn't matter what kind of units. You can think in an example you want. And every time we will have outflow rate of 50. So obviously, if we will have an input rate of 100 and output rate or an output rate of 15, we will get an accumulation of 50 every year, every unit time. Okay, so this is quite clear. Every time we grow with 15 anymore, the mathematical equation is quite simple. Thus, the stock will be the integral of inflow minus outflow plus initial stock. Okay, this is the linear behavior. This is very easy, but it's very unoften. Most of the things doesn't happen in that way. So, just a second example. Imagine that now the inflow is a time function, is 50 plus 50 by time, 50 t time plus 50. And we have an outflow constant of 50. The initial stock is 1000, that's only one. So in this case, as this behavior increases with time, I remember that this is 50 times time t. So there is a significant increase on time of the stock. Okay, because the function is quadratic function. If you do the integral of this function, you will obtain 25 t squared plus the initial value of 1000. But it is not very common, this kind of function. The most common situation is when we have a feedback. The most easy feedback will be just the inflow is not only, let's say, exogenous function or something like that, but inflow depends on the stock. What does it mean? That inflow will be a function of the stock and also a parameter. In this case, parameter is just 0.1. 0.1 by stock. Stock will change with time, of course. And we maintain the outflow constant of 50. How is going to be this behavior? Check that in this behavior, as bigger is the stock, bigger is the inflow. We increase the inflow, we increase the stock. We increase the stock, we increase the inflow. This is what is going to be exponential behavior, even when we have a constant outflow. So, if you check the behavior for these three different cases, this one was the linear, the red one is the time increasing growth, the time function, and the green, the blue is the growth with feedback. If you check the time at 10, with just the 10 units of time, I mean, you can think in minutes, hours, years, whatever, but 10 units of time, these three behaviors are not so different. So at the beginning, well, obviously they are different. This is the growth with feedback, linear, and time depending, but, well, more or less. However, well, in this case I use hours, but it's the same hours that any other unit time, okay? But if you check how is the behavior, not after 10 hours, but after 100, the behavior is like that. In 100, the behavior of the exponential is very, very, very high, while the time increasing or linear constant is very low, obviously in comparison with the exponential. So the exponential behavior is really very different to any other behavior, linear or time increasing. This is something very easy to understand, but sometimes it's not so intuitive. Well, this is the mathematical explanation of why it happens and what time we obtain the double of the value and so on, but I'm going to skip this part. Just give me just an example to understand the intuitive version of that. Imagine you have a sheet of paper, just something like that, and you were able to fold the paper 42 times. It's quite difficult to fold one paper 42 times. But imagine you were able, you have ability to do that very precise, as you fold 42 times. If you are able to do, how will be the thick of the paper after 42 times folded the paper?
2 on.
How thick?
2 on 42.
But give a number. The initial thick is just 0.1 millimeter. So after 24 folders, one time, another, how much will it be? Just give a number. Don't think too much about 1 meter, 2 centimeters, 3 meters. How much? Give me a number. Give me one.
2.253929840.
Okay. You know how to use the. Okay. In order to do that with maths, you can do like that. I suppose you have applied. So, just to show how it is about 384,000 kilometers.
Yes.
More than the distance from here to the moon.
Yes.
So this is so it's not so easy to understand. Just one paper, fold. Wow. So this is one example. If you were able to fold not only 42 times but 100, it will be 50 trillion times the distance to the Earth to the Sun. So just to think about how exponential growth mean. So examples that we model with exponential growth. Examples are real cases, real data. Obviously, they are no like this representation. This is the ideal mathematical exponential growth, okay? But when we have real cases, we try to model real case to this curve, but obviously it's not fit exactly. So this is some examples taken from the business dynamics model of Sterman. So this is, for example, the US GDP, well, in the 20th century, okay? So it may be represented like exponential growth. Another case is the population in prison. Most of the samples are in the United States because Sterman is there. So, but I use these samples because are quite interesting. So this is different because it's the prisoners in United States. In this case, there are a little bit different between the first part and the second part, but it doesn't matter now. Also for the world population, also we can find a different rate in different years, but anyway, this is the exponential behavior in the 20th centuries. And this is a completely different case, is the average growth rate of the microelectronic computers, microelectronic devices. So the density of the number of transistor components in a chip. Okay, so this is a growing tendency also. This is another example, easier than the previous one. Imagine that you have a set of bacteria growing in a bottle, okay? And the bacteria double every minute. So you have one bacteria, after 1 minute you have 2 bacteria, after 2 minutes 4 bacteria, and so on. At 11 o'clock, there is only 1 bacteria in the bottle. At 12 o'clock, we have the bottle completely full of bacteria. So, this is an easy question. At what time the bottle is just half? 11 o'clock, 1 bacteria. 12, full. At what time is half?
11:59.
11:59, okay? This is easy. So, but sometimes it's not so intuitive. We know maths, we know how to do, but it's not so intuitive. Imagine, this is more difficult, that you are a bacteria and you are inside the bottle. When do you be aware about the dangers of the problem? So, you are a bacteria, now only 1, we are 2 bacteria in a bottle, very big, we are comfortable, we still have space. When we were aware about the problem, if we are a bacteria in the bottle, do you think that we were aware of the problem maybe at 11:30? I don't think so. 11:45? No, a lot of space, no problem. 5 minutes before 12? Maybe some of you, I don't know, but more of the bottle will be empty, so don't worry. So, you can guess that this is a metaphor about what is happening with some of our problems.
Yes.
So, when we are aware about our problem, if the problem that we have are growing exponentially. Okay. A new step. Imagine now we have a couple of loops. One reinforced loop, so more stock, more inflow, more inflow, more stock, but a balancing loop. More stock, more outflow, less stock. So we obtain an equilibrium flow here and a stable loop here. But look at the numbers. The numbers are not so different. In flow will be just 0.1 parameter, and outflow will be 0.11. So just 10% of difference between inflow and outflow. It's not so a big difference. However, when we simulate, the units are not very good here, but the behavior is also exponential. So we decrease quickly. Well, there are obviously more cases. Well, this is a different case, sorry. The different behavior is a goal seeking. The goal seeking is when we reach, let's say, a reference value or a final value or whatever. We can obtain this goal seeking behavior with a general system in that way. We have a stock, we have an inflow rate. The inflow depends on stock and inflow rate, but also we have, let's say, a stock reference. Stock reference, you can think in the case of machines, for example, if we fix here the temperature at 27 degrees. So how does the air conditioning system works? When we are behind 27, we give heat or whatever just to reach 27. If we are over 27, the machine works in the opposite sense, so we reach finally an equilibrium or reference mode of 27. So this is what happens in many systems. So usually the behavior is like that. There is a growing rate quickly, but when we are near to the reference value, the growing rate is lower until it reach the final value. Maybe positive or maybe negative or whatever. Okay. The classical behavior is just we have a reference of final value. We find an error between the reference and the real stock, and as a function of f error, we have a different inflow that modify the stock and so on. This is some real patterns of goal seeking, also from Sterman book. This is, for example, the total quality management program. So they they start with the TQM program in order to correct the faults or the defaults rate in the fabrication of semiconductors. So they decrease the number of faults or defects, decreasing until a minimum rate. This is the television share of advertisement in the United States. They increase the number of advertisements until a rate that it was too much, so too many, so they fix the maximum rate of advertisement in TV. This is the traffic fatalities in the United States of per vehicle mile. So they start with a higher number of fatalities, accidents, or something similar, and decrease until a minimum. And this is related with our case, the nuclear plant lower factor. We have been able to increase the nuclear plant load factor until very high values, but obviously it's very difficult to increase much more as other efficiency parameters or whatever. So the next behavior is the oscillation behavior. Oscillation may be due to different situations, but the most common is delays. In this, a delay is just the time lapse between an action and its effect. So we have an action that is a cause, and there will be an effect. Okay, but there is a time delay between both. So This kind of delays are very common in many systems. Some of them I have already explained. For example, emptying a bath, if you want to bath, you need time. Also, the qualification of an exam. You do the exam today, but you will know your qualification maybe in the next week. So this is a information delay. The exam is already done, but you don't know the qualification until maybe 1 week or later. Also, you want to purchase a car. Maybe you decide to purchase a car, but you will obtain the car maybe 1 month later, now 6 months later maybe. Also, the profit of investment. You do the investment today, but you obtain your profit maybe 1 year later or something like that. In the day before, we have talked about very important delays in our case. You decide to build now a wind power plant, okay, you decide now, but the power plant will be worse maybe 2 years later, or 3 years, or 4 years. In the case of nuclear power plant, much more, 5, 10, 15, whatever, okay? So these delays are very, very relevant in order to understand the behavior and to do the plan for the near future. We cannot solve the problem of the energy today in Europe just building a new nuclear power plant, because the nuclear power plant will work maybe in 10 years, at least. So, in the case of climate change, this is very, very, very clear. So, the simplest one of delay is just to have one in time t and time plus x, you will obtain the output. The representation of these delays may be done through first order delay, second order delay, and ampere delay with different differential equations. Indeed, any kind of differential equation has a, let's say, internal delay. Is that we call constant time constant. Okay? So, depending the value of this constant, the delay will be higher or shorter. The reasons I have mentioned may be due just for transportation of matter. We need to transport matter from one point to another, or maybe just delay of information. The information, as the case of the exam I mentioned before. So this is the one of the examples in which we have 3 stocks, and we can introduce delays in different ways. Well, this is how to. Let me shift this part, because we are going to see later how to introduce any kind of things in benzene. And finally, not finally, the next one is the S-shaped growth. The S-shaped growth may be due to the some limits. For example, the classical limit for any biological system may be the carrying capacity. The carrying capacity is the maximum of, let's say, any kind of animal or another kind of plant or whatever in an isolated system, let's say an island or whatever. So, for this case, this is something that we will be able to do later with benzene. We have an initial stock of rabbits, and for these rabbits, we have birds. The number of birds will depend on the initial number of rabbits, the rabbits we have, and also the birth rate. So birth rate multiplied by the rabbits, we have new births, new rabbits every year, for example. And also we will have deaths. The number of deaths will depend on the number of rabbits and the death rate. So multiplying the death rate by the number of rabbits, you will have. But also there will be a carrying capacity. As far as we are near to the carrying capacity, for example, the carrying capacity is established typically by the food. If we don't have enough food, if the rabbits don't have enough food in the island, they will have a lower birth rate, or there will be a lower number of births, and probably they will have a higher number of deaths. So according carrying capacity, or maybe the comparison between carrying capacity and the real number of rabbits, we will modify the number of deaths and the number of births. So in this case, this is also a very realistic situation. The behavior will be like that. When there is no problem, the rabbits grow quickly until they reach, let's say, a quantity that near the carrying capacity. When they are near the carrying capacity, the birth rate decrease, the death rate increase, so they reach a maximum value, usually equilibrium value. This is a typical equilibrium value that we can find in nature in most of ecosystems. In practice, some examples that use Sterman to show this S-shaped behavior is, for example, the adoption of cardiac pacemaker by physicians. At the beginning, the physicians doesn't have enough confidence in doesn't believe in the cardiac pacemaker, so only some of them use it, or maybe they were very expensive. So at the beginning, the growth of the use of this cardiac pacemaker, were very low, but when we are over a certain border, the increase of this use increase a lot. It's a exponential growth, but when we are near to the 100%, obviously the increase is slower until we reach 100, and well, there are no more increase, obviously.
Excuse me.
Yes?
I don't see the difference with goal seeking.
Yes, the difference in the S-shaped growth, at the beginning, the growth is very slow. And this is a exponential growth, but the exponential growth at the beginning is very slow. Imagine you have only this part of the graph, from here to the left. So this is like exponential growth. At the beginning, very, very slow, and then you increase. However, in the goal seeking, this is a positive goal seeking, you grow a lot at the beginning. From the beginning, you grow a lot, and you reach more or less quickly the final value. So the difference is just at the beginning. Here is the same. At the beginning, you grow a lot. In the case of the S value, will be like that. At the beginning, it's slow, then go quickly, and then like that. So finally, well, another example of this. Well, this is the growth of sunflowers. It's a completely different case. So at the beginning, slowly, and then, well, quickly, more or less, and then slowly, quickly, and then reach a value. But the point that I want to remark here is that all these cases are not exactly as shaped. They are not mathematical like that. They are not like this. Okay, this is a mathematical curve with very precise. This is a behavior similar to this S-shape. This is what we are going to model. In practice, the data that we are going to find are not going to fit like that, obviously. The data we are going to find and we will need to fit will be similar to this one, okay? And we have to figure out how to model with this data, those data. Okay. Well, the logistic model for population with carrying capacity from a mathematical point of view will be something like that, but I am not going to get deep in that. This is the growing of population with carrying capacity limit, and this is the net growth. The net growth is just the derivative of this curve, of course. So if you check the net growth is similar to the behavior that we call collapse. At the beginning, a higher growth, then collapse, and a higher decrease until it reaches zero value. This curve is just the derivative of this one, okay? But this is a different behavior for the derivative. This is also a classical example. Obviously, nobody knows exactly how it's going to be evolved the curve, but it has been used to model sometimes the peak oil, natural gas oil, or whatever. Natural gas peak, sorry, or even any material peak. So we have an increase of the consumption of any fuel, and then we reach the maximum production, and then they decrease the production. We don't know exactly how and where, but it is predicted that the production is going to decrease in a certain way. So we can model this kind of curves through this kind of simple model. We have accumulated extraction, we have a real reserves, we have a rate for oil extraction. So according the parameters we use here, the maximum reserve we have, and the parameter of maximum extraction, we obtain curves like that. This is for oil extraction, this is for accumulated extraction. And as you can see, this is similar, this is similar in the form to the peak oil curves of many authors. Another different case, also with the, in this case, the S-shaped growth or collapse, is also for epidemics. In epidemics, there is usually an increase of the number of epidemic case, infections case, and then we reach a maximum and then decrease. This is a model. We will check also with Benzina a similar model to this one in the session after the lunch for any kind of infection. Obviously, the infections may vary depending on several parameters, but more or less the general terms, we have a susceptible population that is able to be infected by epidemia. Then some of them are infected depending what is the infection rate. The infection rate will depend also on the contact rate. This is the reason we keep in our homes in order to reduce the contact. Also the infectivity, these kind of parameters. And then we will have a stock with the people that are already infected. And after some time, this sometime will depend on the average duration, these people will be recovered and will go to the stock of recovered people. Okay, these are the more or less common equations, but we will check another more precise equations. Obviously, depends on the time of infection. This is here is one of the models for infections, and this is the classical behavior. Very big, very quick increase and then decrease, like a collapse. People that are susceptible, people that are infected and recover. So the next behavior is the growth with overshoot and collapse. I'm going to explain. This is something that maybe happened with a population in which we have also some need of food, obviously. So we have a reinforced loop for growth according more population, more growth rate, you know. But more population will be more deficit of food. The deficit of food will be related with the carrying capacity, and the result, as I have shown you, is a curve like that. Also, there are some delays. We represent usually delays in the arrows through a couple of parallel lines perpendicular to the previous one. This means delays. So the effect of the carrying capacity has a delay over the deficit in that case, and the deficit has a delay over the growth. We will explain this kind of delays with our causality case later. This kind of delays has a consequence of a oscillation in the behavior. This oscillation is something that, for example, we can find in the behavior on some prices in the market. Maybe there is enough products in the market, but we cannot get. So the price is increasing, but when you get the product, the price decrease. So maybe you collapse the market, the price increase again. So these kind of oscillations are usually due to delays. Delays maybe by, as I said before, just by transport, or maybe transport of material transport, or maybe just for information. Just this is the same classical behavior after an input overshoot and then a new equilibrium value when we change, for example, in that case, the reference value. There were an equilibrium in this point, but we change the reference value, then we reach a different equilibrium, but the transition between this point and this new one, we have an overshoot. This is when something is abruptly changed in the system. In this case, the abrupt change is due to the reference value. For example, if we decide, we have this island with rabbits, and then we introduce, let's say, a big quantity of food in one moment. So the rabbits have much more food, the rabbits can grow a lot, but then, again, they will find a new limit, okay? Well, this is also when we have, in this case, excessive exploitation of the resources we have, resources like food or whatever, in our case. Well, another example, but I don't know if I can shift this part. Well, this is another example, but more for economy, just the production, labor, productivity. Well, I'm going to explain anyway. This is a different example of the environmental, but we can use it anyway. Imagine we have, let's say, a company that produces anything, like tables or chairs or whatever, or computers. So we have a production, the production increased our stock of tables, so we have sales, and the sales that we have yearly are a reference to decide what is going to be our desired production. Obviously, our desired production should be similar to the number of sales we have every year, or every month, or every week. So we have to adapt the desired production to the sales we forecast to have in the next time. So if we have a forecasting of the sales for the 3 months that is going to be double than we have now, we have to modify the production to have double production in order to have double sales. So the production will depend of at least, in this very simple example, of course, will depend on 2 variables, productivity and labor force. So productivity and labor force will determine, in this very simple case, the production. So we decide what is the desired production according to the forecasting of sales. If we check that the sales are increasing a lot, or For example, in our case, if we detect that the energy demand is increasing, we will need to plan a new desired production for the future. So according to this desired production for the future, we will decide a desired labor. So we will need to hire people. Obviously, in order to hire people, we will need some time to correct the labor. So if we decide to hire people now, we will need at least maybe 1 month, 2 months to have those people working. So this is a delay between how many workers I need and how many workers I'm going to really have working. So this delay is going to be relevant. And finally, I will have the production with, assuming a constant productivity, or no constant maybe, and the sales, and so on. We will have also a desired stock. The desired stock, we will need also some time to correct. So the desired stock is just to have a regular answer to a system like that. The behavior is like that. So we have a labor force more or less constant, but in that point, in one point, I decide, okay, I'm going to increase sales in the near time, in 2 weeks or in 2 months, so that they need more labor force. However, I try to hire more people, but then it's too much and so on. But because no, this is not the labor, this is the labor. So there are oscillation due to the delay, and this is the stock. This is more clear. At the beginning, I have more sales, so I decrease the stock. Then I have more production. I increase the production, increase the stock, but I have more sales until I reach an equilibrium point. Well, this is some more or less real examples of the same book. From Sterman, this is the population of London. Increase, then reach maximum, and then decrease. Aluminium production at the United States, increase, and then decrease. This can be similar to the peak of aluminium in United States, maybe. Okay. Anyway, again, I must mark the situation that there are oscillations and the data are not so soft. Obviously, there are real data. Well, this is the other example I already mentioned before about the rabbits and the carrying capacity. The carrying capacity, obviously, usually is due to the abundance of food. Abundance of food may be the plants, but the plants has also their own dynamics. So the plants grow with a certain growth rate, and death usually when rabbits death the plants. Okay. So in this case, we have 2 different stocks, and there is a let's say equilibrium between them. This is according, obviously, it depends of the parameters we use here. We can modify the rate growth here, we can obtain this kind of behavior. At the beginning, there is an increase of the number of a big quantity of food, there is no problem. So the population of rabbits grow a lot, but a certain quantity, there are a growing rate higher of the rabbits than the maximum production of food. So they eat a lot of food. The decrease of food is very quickly. At the beginning, the rabbits, they still grow a little bit because at this moment they still have food, even when this is decreasing, but they still have food, so they still grow. But when the food decrease, they cannot support so scarcity of food, and they die abruptly. So there is a collapse of the population. This is a mathematical case. Don't worry about metaphors now. At the moment,
rabbits.
don't moment. No, but maybe you may be worried about the metaphor. Okay. So another classical case to study this collapse behavior is the Easter Island. Everybody knows the case of Easter Island. There is a lot of literature about why this civilization collapsed. Maybe I like a lot the book of Jared Diamond about collapse. Probably you know. If not, I recommend you the lecture, the reading of this book. We have done this exercise, but I'm not going to show you the exercises now. Okay? Any easy question by now? Or I can start with the introduction to benzene software. We have easy questions?
LOCOMOTION.
What?
LOCOMOTION model.
Yes, we can show also the LOCOMOTION model. LOCOMOTION model is used for the prey-predator model. It's quite similar to this rabbit, for example, with rabbit and foxes. I'm going to use it. It's quite similar. Well, indeed, it's based on LOCOMOTION model, the prey-predator
Yes,
model.
model.
Yeah. Any easy question? Okay. I go ahead with the still theoretical introduction to benzene, and after lunch practical benzene. No, this is the not just half an hour. Yes. So, as far as we need to change the computer for the practical issues, we still have half an hour before lunch. So this half an hour is going to be mainly with the slides, and after lunch I change computer to do the practical issues with benzene. Anyway, if you want to start in your computers with benzene, the things that we are going to talk, you will see in your computers. Okay? So, obviously this is again a very short introduction to benzene software. All the things that I am going to talk are taken from the user guide of benzene software, so you can read the original benzene manual, of course. It's much more clear and explain everything, and you can download this manual from here. Well, you can download. Now there is no PDF, there's an online help, but anyway you can read online in the web page, and it's very easy to manage and to understand. Okay? So, what is benzene? Benzene is a visual modeling tool that allows us to conceptualize, document, simulate, analyze, and optimize model of dynamic systems. I'm going to stop in each of the words. We can just only conceptualize. We can draw something like that. So we draw the relations, no equations, just to understand or to discuss the relations. Just like a drawing tool, nothing more. Second, we can document. It's quite useful because you can document all the relations or the model. Even there are some additional tools for document. I forgot, by the way, to install this document tool in my computer, but I can show you, I can give you the web page where you can download an additional tool for document that is free also. Obviously, and probably it will be the main purpose of this software. You can simulate any model, run the model and see what are the results and so on. You can analyze, for example, in the case of William or Medeas, maybe you can, it's quite interesting just to analyze what does it mean, what are the variables, the input, the output, how many loops do we have. So you can check many things in a model that is already built. You don't need to build a new model. You can work with something that has been already done, just trying to understand. And also you can optimize model in several senses, maybe not in the same sense that Ilya was talking yesterday, but you can optimize the models in different ways. For example, you can check from all the variables you have, what are the more meaningful and what are the non-relevant. So you can say, okay, if I change this variable, the results is the same. So take out the variable, it's nothing to do. For example, this is a way to optimize. Another way to optimize, we are not able to get deeper in that, but you can try to fit the best parameters just to fit with the real data in an automatical way. You can check real data and it is able to find the optimal parameter for simple cases usually. So, and in order to do that, obviously, the methodology that is in the underground of this software is system dynamics. So we usually use stocks, flows, and auxiliary variables. That are the type of variables we mentioned in the previous session. So, Benzene try to connect words will be the variables, and with arrows, relationships among system variables, and record all the connections. All the information will be able to introduce in Benzene through that is called equation editor. In the equation editor, you will find obviously all the regular function that you may use. We will see any kind of function you will be introduced. Obviously, we can introduce linear, non-linear functions, even tables. Tables is quite useful to check for experimental data, for example, or something like that. In the analysis tools, we will see that we are able to look for the causes and the consequences of each variable, and also to check any kind of loop that we have, stability, sensitivity analysis we will be able to do, and so on. Usually, the steps that we will follow in order to model a system will be the same steps that we explained in theory. So the starting point of any kind of model is not just open Benzene and try to introduce variables. The starting point is just to think about what I want to do, what is the problem I want to solve, what are the main variables. For example, in my case, usually I start the model and I develop most of the work of the problem with a paper. Maybe I am too old, but anyway, for example, yesterday I was working a little bit with Gonzalo, I was working with a paper and a pencil, and when I have ideas clear, I go to the computer. So anyway, you can go to the computer if you want, but what is my recommendation is that you need to think about the problem and the variables before going to program anything, okay? Just to, so the first, usually we develop an influence diagram. This is the influence diagram, for example, for population, births, mortality. When we have the influence diagram and we know what we want to do, sorry because this is in Spanish, then we go, the second step, go to Benzene to program stock and births, birth rate and so on. But first step, think about what we want to do. This is what we are going to follow for the case of the calle identity. So, Benzene is also a graphic programming environment, so most of the things are doing by graphicals. At the end, you need to introduce equations, of course, but most of the information we try to put in a graphical mode that is easy to understand, to see, to learn. Obviously, the functions you have to introduce includes any kind of mathematical function, logical functions, whatever. Okay. And finally, of course, we have a relative big number of ways to watch or observe the results. Usually, the most friendly way to watch the results are in graphical mode. So we show the behavior with curves, different colors, and so on. But also we can check also the real values in table, in Excel files, whatever. Okay. And obviously we also can analyze models that have been already done. There are several versions of Benzene in order to understand. If you get deeper with that, the last version I know, I think, is the 9.3.3. I think this is the last one. There are a free version for academic use. One of the ones you have already downloaded is the TLI. Then there are other versions that you need to pay for that. PL Plus, in this case, you can add to the previous properties, sensitivity analysis, and reading of Excel file. This is something that we are going to use. So we cannot do the sensitivity analysis and the reading of Excel file with the free version. Then there is a professional version with optimization, vector arrays, subscripts, and so on. And there is the most complete version, DSS, that is the one we use for the development of the data and so on. Then again, there is a model reader that is free. This model reader, completely free, you can open any model, any one, you can read any one, and you can run any model. So from this point of view, it's quite useful for you. There are also a couple of additional tools, but we are not going to talk about that, about runtime application and Sable for some graphical interface, but they are not using anymore, so not relevant. Well, this is you have already Benzene and you have tried to open. You will find some windows like that. Well, the graphical user interface has changed. Unfortunately for me, I can change to the old one and the new one, so I prefer still the old one. This is the old one. If you open by itself, you will see a different mode. The different mode, the icons are funny, more funny. But if you want, you can change to this mode. Later I will show you. This first overview of the graphical user interface is more or less as most of the Windows-based programs. So you have a title bar with the classical functions for file, edition, view, model, and so on. Then you come some tools, the main tools that we use, like open file, look for file, put, copy, and so on. Then here you will have the main tools for running the simulation. We will see later different modes for running, but there is a basic way for running. You run the simulation and just all. But we have the second one that is very useful because you do the simulation time by time and you can check any change in the model. We will see later. Well, others that are a little bit more complex. Here, usually in this bar, we have some analysis tools. In the analysis tools includes the possibility, of course, to check the graphs of any variable. but also to analyze the causal tree. If you have a variable, what are the causes of this variable, and also the consequences of the variable. Also, you can check data in different ways and so on. Well, but I think this is much easier to see with the real software than not with the slides. I don't know if we will be able to change or to stop here, because this part I can tell you, but it's much more easier if we run the model. It's very difficult to change again. Well, maybe or we can stop here now. What do you prefer? Well, I can.
We can try to switch.
But it's only for 15 minutes. What do you think? Switch. Okay.
Absolutely.
We can switch to the other computer. Okay. I go to the.
You're rotating the French. Can you send me this? No.
English.
It's a mix.
Yeah.
They cannot translate. Amazing.
That's weird. It is English.
No. Okay. No, sure. Silence. Yes. Okay. Okay. Okay, thank you. So if you start running benzene, everybody has started running benzene on the computer. So the graphical user interface you will see will be something similar to this one, at least the style. Maybe you will have less options because it's the free version, but the style will be something like that. If you don't mind, I hope I switch in tools. I am going to switch to the old graphical user interface. So I see like that. But it doesn't matter, it's the same, of course. There's only the style of the graphs and so on. So I was explaining how the software is. You have a toolbar here with the main tools, open, save, and so on. And here the analysis tools. Well, let's start with the most easy way to start is just to try to build our first model for those that haven't built a model on benzene before. So the easiest model is the population model. Population model we have seen already several times. The simplest way is just to choose population variable, growth rate, death rate, and we have these three variables. So, as you can see, you know, growth increased population, population increased growth rate, population increased the death rate, and death decreased the population. So, in order to do that we have already seen several times in the screen, how we are going to do. First, we decide to do a new model. You go to the File option, the basic parameters of your model. You don't need to change the basic parameter, and time step means the resolution of the differential equations to the problems we have with time step. As unit type, I don't know if you are familiar, the basic integration is Euler. Usually for our experiments is enough, but you can have a Runge-Kutta 4, for example, that is obviously with the error is lower, the precision, but you don't need. So Euler is enough, usually, at least for this part. Okay, and this is the initial. Now we can start.
You have
Is it
more.
even professional version?
You don't have this?
In this version, we only have one very small.
Okay.
Sí, está haciendo claro con aquí.
Yeah, sorry, because we. Okay.
Yeah, so.
You have units. Euler. So, okay, you have less options, but the basic options you have. So, sorry, in my computer I have the complete version. I went. Well, anyway, the option of initial time, final time, integration type you already have, and units also you have here. That's enough. Don't worry about that. So the next point, usually the main variable to choose is just the one that we are considering the stock. Our stock is going to be population. You can think about world population. So for example, here with the mouse and tick where is level. T, there is a T level here. You see here. You click one time and then go to the screen, to the main, to start with the variable population. So you click and you can type population variable. Population with the name you want.
If you have any question, raise the hands and I can
Yes.
help you.
For example, I wrote population here. Everybody can follow. If anyone has problems, please hand out your
Gonzalo, you have to be present.
Gonzalo is
And-
okay if you
yes.
have stock 2 and then you take stock 2 and write.
yes.
Because you have variable 2 and stock 2. Variable, so, yeah. And so.
Yeah, you have.
So you will have something like that,
And
and this is our population stock. Now, after population stock, we will need two different flows, one inflow and one outflow. For outflows, we go again with the mouse and click on rate. Okay, here. Okay, then click on the left of population. For example, here, one time, then appear a cloud, something like that. Go through the population box, click again, and then you can write the name of the flow. In this case, the name may be growth, growth, or whatever, pop growth, for example. Okay? Or birds. Birds? You prefer birds? Okay. Birds. Okay. And then, again, for outflow, you click first on the stock population for outflow, then go with the mouse to the right, click again in any place, and then you can write the name of the outflow. In this case, deaths. Okay? You will have something like that. One inflow for birds, one outflow for deaths. Okay? Gonzalo can solve all your problems. Not your life.
Population problem.
Okay. This is the basic inflow, outflow. But birds is just a derivative. Usually we will need a parameter to define birds. For example, birth rate. Okay? So we will need at least a couple of auxiliary variables. Birth rates and, for example, average life, something like, or expected life, or something like that. For auxiliary variables, we click on variables. Where is the A? Okay, here. And then click again in any place. And I wrote here
Expected, life expectancy.
birth rate and maybe average life you will have something like that. These are the main variables. We are going to use just these variables, no more. And now we have two flows, but we can establish more relations. What relations we have? Obviously, we will have a relation between the birth rate and the births. So we go to the arrow symbol, click on the arrow symbol, then click on birth rate, go with their mouse to the births and click again on births, and you will have an arrow from birth rate to births. You can do the same between average life, click on average life, click again on deaths, and you will have something like that. Everybody has that?
Yes.
Okay, our graphical model may be complete, but obviously there is no date, no equations, nothing. Well, there are some equations. Internally, when we choose that births is going to be a flow population, it already choose that there is an integral of that. So, in order to introduce equations, we use the symbol fx, function of x, okay? This one, okay? If you click on this, now you appear that everything is in black mode. You check that everything is black. Black means that there is no equations, nothing to do, so you need to give some information about everything that is on black. So we can start with population. We click on population, and then there will be appear an equation editor of equations. I hope it will be similar to the one and I can choose. When you go to this editor, you can see that the name of the variable is already done, the name population. Obviously, if you want, you can change. It's important that, as I mentioned before, we what kind of population we want. Or individuals, persons, okay, units, persons. For any kind of integral, we need the initial value, isn't it? So we need to introduce here, sorry, initial value. Initial value, how is the world population today? About?
So this is our website. You can see the website.
Yes, but anyway, 7,000 or 8,000 million? Nearly 8,000, isn't it? Let me check somewhat.
7.97 billion.
7.97
billion. 8 billion.
97. Okay. Nearly 8,000 people. Now, we can introduce the next, the birth rate. What is the birth rate?
The number of births per person.
Per person of
Per year.
per year. No, the birth rate is just, well, maybe let's start. What is the number of births? Births will depend on birth rate and population. So we will need an arrow from population to births, because we will have more births if we have more population. Births will be just the product between population and birth rate, isn't it? And also for deaths. Deaths will depend on population. So you can click on arrow, click on population, and then click on births, click population, click on deaths. Okay?
Okay.
Now, coming back to the function, we will need to define the number of births. Births is a flow, so first units. Units will be persons per year, maybe. Persons per year, okay? And in the editor, you can see that here you have already chosen the variables which are related with births. You have already here birth rate and population. You see? So, we can just click on one of them. It's easier just to click on the variable instead to write.
Wait. Yeah, let's see if everybody catch up to then.
Okay.
Does everybody have like this? Is everybody that far? So, can you open the diagram? Yeah.
Everybody can what point you are.
For me, population.
Okay, and then now close this. No, not close. Pare, multiply. No. That's okay. The lines are.
What did you wrote in? No, where did it? The black.
No, it's not a black. It's just like that.
Birth rate, there is nothing for now.
No symbol.
Yeah, there is no.
¿Has cambiado birth rate?
Que se me quedó la frente.
No, not yet. Not yet. Not yet. I am going to be slow, just. When we go again to function, we go to births. So in order to, I lost units. Don't worry. Persons per year. Then the births will be population What happens? Population multiply birth rate. Obviously, you can write by yourself population, but you can mistake one letter or something like that, so it's easier to click. So when you finish, one thing you can do always is just check syntax. You can see the down part of the editor. Check syntax. Check syntax, and you obtain in the line errors. equation okay here. Okay, you also can check model, but now it's too soon to check model. When you finish, you say okay, and the same for debts. Debts, we can, obviously debts are the same units. Now you have already persons per year. You can choose in the toolbar. So I have introduced before persons year. So I can choose now persons year for debts. And for the equation, maybe the number of debts in a very general way will be just population divided average life. This is an approximation, of course. Okay? Okay.
It's 1:05, so maybe we can
Stop.
stop,
Yeah.
and go for lunch, and then we can.
Okay.
If anyone, please, if you didn't sign your sign-in sheet, and if you didn't sign for Saturday, please do so now.
You want, before you leaving, remember to save the file. Save as any name. No.